So now we're going to discuss the concept of aromaticity in the carbanion. So I have here got a carbanion attached to a benzene ring. So being a negative charge in conjugation with the pi, it is going to show resonance. There is going to be delocalization or the shifting of the negative charge or the pi electrons. So let us begin. This negative charge is going to come down here, pushing the pi bond here. And now we've got a negative charge over this on this place, and we've got a double bond here. The bonds, two bonds remain in the same place, which is this one and this one respectively, and we've got a negative charge. So now there is more moving of this particular charge, and what I'm getting is that this negative charge is gonna travel a little further. Please remember to put the resonating, the sign which tells us that these all are resonating structures. Okay, so moving on, this negative charge will now land at this position. So we've got a double bond at this place and a double bond at this place, which was at its original location. Moving forward, this negative charge, what is going to do is it is going to further move for us, pushing the pi bond again, and these all are resonating structures. So this negative charge is going to actually land here, and now we have something. This is double bond here, a double bond here, and a negative charge here. So all of them are actually nothing but resonating structures. Okay, so what happens next is this negative charge now finally comes back home. Okay, we're forgetting the double bond here. So let us just place them. And now what we see is that the negative charge is finally back home to its CH2 where it originally all began. And we have got the double bonds at a new place. So this is how resonance occurs. And this is one more resonating structure that we have. Now, what happens is that you have noticed, or you may have noticed in this particular example here, that the negative charge is only traveling to a certain number of places and not everywhere. So where are they traveling? The negative charge comes here, the negative charge is coming to this place, and the negative charge is coming to this place. So we can highlight three areas, three positions where the negative charge lands. And you can see that the resonating structure, let us name them 1, 2, 3, 4, and the fifth one. Okay, so the resonating structures 2 and 4 have the negative charge at the same position, which is known as the ortho position. So here we have negative charge at ortho, here we have negative charge at para, and here we again have the negative charge at ortho position. Okay, this is the ortho position, meta position, and this is the para position. So moving on, so we notice that the negative charge only goes to ortho and para position. That was what we were after. So the negative charge is going to two places, ortho and para. Now, because the negative charge is traveling at that place, so we can conclude that resonance travels only at ortho and para position. So I will have resonance only at these two positions, and we have to keep in mind and not at meta position. So resonance only occurs at ortho and para position and not at meta. Now, why I wanted to highlight this particular part is that when I come to the next question, here this point is going to be of value to us. Now, let us just see that we have here in front of us first, second, and third. Okay, so we have three compounds here and we have to tell the order of stability. Okay, so let us just say that we'll start by writing the effects. In these cases where we have to tell the stability, we start by writing the effects in each of these species. Now let us begin. So if I am concerned with a resonance effect, I see that there is a negative charge and I have got double bond in this whole region inside. This circle actually highlights that we have electron density inside the whole body of the benzene. Okay, so what I notice is this negative charge, and we have done in the previous case here, I have noticed that resonance travels only at ortho and para position. So what I'm gonna do is, because this is the para position, this here is the para position, this here is the ortho position. So I am gonna write that plus M effect, that resonance will only occur at this. And since CH3 is an group which donates electron, so of course it is going to show a plus M effect. So I'm going to say that this first one will have a plus M effect. The second one will not, because the CH3 is at meta position, but the third one here again has at ortho position, the CH3, so it again shows a plus M effect. Okay, now inductive effect. Since inductive effect travels through sigma bond and not through the pi bond, as in the case of resonance, so inductive effect will be everywhere. And since CH3 is an electron donating group again, so it is gonna show plus I effect. Similarly, we have plus I effect here also, and we have got a plus I effect here also. So we have got plus I effect and we have got the plus M effect in two of them. So let us just decide which one is going to be stable to the maximum extent. Now, if I look back at the example here, I notice that the negative charge is traveling to all the ortho and para position equally. So the plus M effect will have the same effect wherever it is, whether it is at ortho or whether it is at para. So the resonance effect, the resonance will be equal, the amount of negative charge, because the amount of negative charge is same everywhere. So we can just say that plus M is same at ortho and para. At both the positions, we have the same plus M. But we know that plus I, there is another effect which is the plus I everywhere. The plus I decreases with distance. So what I'm going to do is I'm just going to give them numbers that highlight the amount of electron donation that they are actually contributing to the particular species. So what happens is that in first and the third case, I have got plus m. So plus m is actually to the same extent. So let us say that we have got 5 units of plus m, and similarly we have got 5. Similarly, we have got 5 units of plus m at the third one too. Now, since plus I is depending on distance, so we notice that the distance is the least here. Distance is least in the third case and maximum in the first case. So what I do is if I'm to give a number to the plus I, this is gonna have the maximum, give the maximum plus I. So let us just say it is giving a plus 10. This is giving a little less, so let us take it as plus 8. And this is giving the least plus I, so let us take it as plus 6, just decreasing 2 2 in each. Now in plus 3, the plus I is highest because the distance is the least. So now I have to decide the stability of them. I am not singling out anything. Why? Because plus m and plus I, they both are electron donors. We know that plus I also gives electron, and plus m also contributes electrons. So plus m and plus I both are electron donors. So they decrease the stability. That is what we have been concerned about for the whole question. So they are both are decreasing the stability of carbanion as they increase the negative charge. So both of them are decreasing the stability as they are increasing the charge, the negative charge on the particular species. So we have got plus m and plus I, and they both are decreasing the stability of the anion. Now let us decide on the stability of the species. Now, why have I given the numbers to them? So that I have a ballpark figure, or I can decide which one is going to give the maximum amount of electrons to it. Now let us just total this amount to give us a better understanding. So notice that I have a plus 6 here and a 5 unit here. So this amounts to a total of 11 units. So 11 units of, this is all hypothetical. That is actually not the charge, but I'm just considering it hypothetically so that I can understand. I can make myself understand. So 11 electrons. So 11 charge. It is actually giving, contributing electrons to this and making it more unstable. This has a contribution of 8 and this has a contribution of 15. So maximum destabilization is going to be caused by this third one here. Okay, because it has both the plus m and the minus and the plus I effect. Also, the plus I is the nearest to it. The second one doesn't have a plus I effect, so we can say that it is giving less electron donation to the carbon ion and therefore becomes the most stable out of all of them. So if I'm writing the stability order, the second one is already winning the race because it has got no plus M effect. So therefore it wins the race. So it is only giving electrons by a plus I effect. Now in the first one, we have got plus M as well as plus I, but the plus I is giving less electrons because it has got a greater distance to cover. So the stability is in the order that 2 is greater than the first one is greater than the third one. So notice how when deciding on a little figures by ourselves, we have got the answer to the question by just deciding how the electron contribution will be occurring if we just giving them numbers. Okay, so I've got the stability order that the second one is winning the race, followed by the first one and the third one. So this is the order of stability.